So I got a couple of these GeeekPi LCD displays that speak I2C. I'll have a link down below. What these are this Hitachi HD 44780 paired with a PCF 8574T that handles the I2C communication. One thing I'll note right off the bat is that while information on these LCDs say that it'll run on either 3.3 volts or 5 volts, with the contrast settings on this package, it is basically unreadable on 3.3 volts. The logic still works, but to get enough contrast, the LCD really needs 5 volts. The LCD can be set to run in a 4-bit mode, and the microcontroller add-on expects to use this 4-bit mode. LCD has 11 pins on it. 8 are for data. That'd be these ones here. And since I2C works on 8-bit packets, 4 data pins and the 3 control pins that it also uses, that comes out to 7 bits to control the LCD display. According to the data sheet, the data pins are going to be these pins 4 through 7 because the other ones are not used in 4-bit operation. Let's see here. So another thing to note is that in 4-bit mode, the 4 bits have to be transferred twice. And when sending commands, here. So when sending commands, there's a table here with all the formats, and on the next page here, it'll mention that to write data, this RS bit has to be set. And so for the other ones, there's going to be some, first bit for like doing the entry mode, and then some options. Another bit here, this will set for display, and then some options. And so that's how you can sort of set these things up. And it also has an option to sort of put in custom characters. There's a basic font package that comes with it. The one that I got seemed to have, let's see, I think it's somewhere up here. It's like a combination ASCII and Japanese. Yeah, this one here is the one that came with mine. Because if you go out beyond sort of the standard ASCII characters, you start getting some of these old Japanese ones. I found some example code, but maybe it was meant for a different version or manufacturer. I ended up having to run several tests to get all the bits lined up. So the LCD backlight is not handled by the LCD's logic. It's handled by the add-on controller. So a plain I2C packet with the backlight bit set to 1 turns the backlight on, and a packet that's all zeros would turn the backlight off. To keep the backlight on, every packet sent has to have the backlight bit set to 1. And the backlight bit is bit 3. Bit 0 is that RS or register select pin. 1 is the read-write pin. And 2 is the enable pin. Then bits 4 through 7 correspond to data pins 4 through 7. Since the commands are 8 bits long, they need to be broken into 2, and the upper 4 bits are sent first. And since 4-bit operations have to be sent twice, they are first sent with the enable pin set to 1, and then sent again with the enable pin set to 0. So every command takes 4 writes. The upper bits twice, then the lower bits twice. So I started to put together a file system to talk to the LCD through files. And I played around with various settings on the LCD to figure out what it was capable of. And being a rather simple device, it couldn't do a whole lot. It can be set to automatically jump down to the next row, but only after 40 characters have been entered. And if more than 40 characters were put in on the bottom row, it would jump back up to the top row. And it by default, it wouldn't display all those 40 characters. It is possible to make them sort of scroll around back and forth one way or the other. But if you want something that works like a basic console, you'd need to make your own buffer and do the logic to reprint the text of row 2 up to row 1 and then start printing again on row 2. The LCD does automatically print in the next cell after each character that is sent to it, so there's no additional command needed to move a cursor. Every time you just send a letter to it, it'll just put it in the next available cell on the row. But the starting point of the cursor can be moved to a specific place with a command, and the cursor can be displayed with an underscore or a blinking square. What I settled on was treating each row as a separate file. That gives 16 characters on each row, and this will work well for displaying general information. If you print some text into row 1, it will stay there, and then you can put more frequently updated text into row 2. Basically, this allows each row to be changed independently without having to send some specific command to change rows. So you could do something like make a script that will write CPU temp into row 1, then periodically copy the text of the CPU temp device file to the second row. Another thing, this thing can be configured to print either left to right or right to left, and scroll the text in from either side if you want. So what does an LCD look like as a file system? Starting off in main here, I set some defaults, like for the serve name, the mount point, and the file that will have the I2C device. I also allow entering in alternate names for those things. So it'll go down first and run this little initfs thing. It'll then run this LCD init function, and then this thread post mount serve actually packages up the whole thing and puts it in the serve directory, so it can then later be mounted into the file system. So the initfs function is one I've recycled through a few different projects. What it does is it takes a name, and that'll be your name for the what you want to name the directory. So it'll get the user who invoked the program and store it here. As s.tree, this is for a serve SRV struct. Serve has this tree thing in it and pointers to all the 9 protocol commands. And in tree is a file struct called root. So we call that here. I have my own local version of it. So we do an alloc tree, and this will basically set up, that tree structure, and it'll pass to it the user. The group is going to be the user's group, and some initial sort of mode settings, as well as an optional pointer for a destroy function, which we're not using here. Next, it does a create file. This is going to be creating a file on root with the directory name owned by the user, and this is saying here that this file we're creating is actually a directory, and with the mode, it'll also have there's an option to put more pointers, but we're not using that here. And then just a little sort of sanity check thing. Something to keep in mind, these alloc tree and create file do run malloc, memory allocation. So that's one of the reasons you want to check to make sure that it actually allocated the memory. And if you go about trying to do lots of creating files and stuff dynamically, you'll want to make sure that if you get rid of them, that you use the proper functions for doing that to free up the memory. But anyway, the create file here returns a pointer to a file type. And then later down here, what we're doing, this might be a little bit better if I widen it out. We're running through a little for loop here. I have a little thing for the files. It's going to go through the number of elements, and it's going to create a file in this directory with the file's name, the user, the mode settings, and it will put a pointer back in there too for this files. So it runs through this loop and puts in all the files from the struct I made. So I have that up at the top here. Not that high up. Here we go. So here's my little dev file struct where I set a name, a couple function pointers for what to do on a write and a read. And here I set those up. So I'll have a control file, row 1 and 2, pointers to various functions, and then their modes. So for these two row files, they're going to do nothing on a read. If a write is called on them, they'll run this write char function. And down here, there's this, mentioned it before, the little serve struct. So you can take the default pointers that it assigns, or you can assign your own. And so I'm going to assign my own for the read and write. So for writes, I'm going to set it up here. Of my little dev file thing. For write, I'm going to check right off the bat if it's a 0. So if the nothing's being written, it's just going to go ahead and bail out right here. Otherwise, it pulls the that dev file out, which was set as one of those pointers earlier. That puts it in this sort of aux here. It's going to pull that back out, and it's going to respond to the request with the whatever the do write function is for that file. The second argument in respond, so respond, it'll have a request, and then the second thing is actually a error message. So my write requests will are set up to return characters. So if there's something wrong, I can just write out an actual error message there, or if everything goes, according to plan, it will just return nil. So let's see what actually is my write file. All right. So this is the write char command anytime a write is done on row 1 or 2. And well, first thing I do is I get the name of the file being requested here. And the reason I do that is I check to see if it's file row 1 or row 2. If it's row 2, I drop down to what's technically row 1. And if it's row 1, it's going to be row 0, and that will set the position of the cursor down to the next row or to the very top. Also, another thing is that since I'm just writing, I'm just using the 16 characters and not bothering with scrolling around. If more than, 16 bytes of data comes in, I just truncate that to 16. Next thing is I have a little function that will set the cursor to home on whatever row has been set. And then after that is just going through the incoming data. That's this if call.data. I have it set right now so that if it's anything other than the just sort of standard printable ASCII characters, it'll replace it with a space instead. And then it sends it out to the command to actually print a character to the LCD. Any request for writes is going to expect the amount of characters actually written to be returned, and the general file system will keep track of that, and if they don't match, it will throw an error. So I also make sure that if it's under 16, it'll go ahead and return whatever was printed. So I do keep track of that. If for whatever reason someone prints more than 16 characters, just to not bother with any sort of errors. I just have it say that it'll just confirm that everything that you wanted written was written, and set that. And then since there's no errors, just return nil. So this is my little function here for writing characters out. Like I said before, the LCD is running in 4-bit mode, so I have to split the command into 2 parts. So that's what's masking out here, is that sort of upper 4 bits, and then it shifts it over 4 and masks it again for the second one. So another thing to keep in mind too is that backlight bit, since it's controlled by the little add-on microcontroller, has to be set to 1 on every command if you want the backlight to stay on. If any command gets sent where this bit will be 0, the backlight will turn off or flicker. The other thing is that this register set bit has to be set to do any sort of data prints. So I have the other one up here for if I just want to send a command to, like, say, turn the blinker on or the cursor or clear the screen. I still set the backlight bit, but not the RS bit. And then once I've sort of built up each one, split the 4 bits and the other mode bits out, put it all together, send it to command 1 and 2, and then I call this function here. So yeah, this is where each 4 bit's going to be sent twice. The first one with the enable bit set, and the second one with the enable bit set to 0. And there was some stuff in there about like a certain amount of downtime, so I just put in a small sleep thing between each command. So yeah, this is how, and every time you'd write a character, you technically have to write or send a command. You'd see that like the command has to be split into 1/2, sent twice, and then the second half ends up getting written twice. But yeah, so you just have to remember that on this thing, the controller though will see this LCD bit on each of those 4 writes, and so if it isn't set to 1 on all of them, it'll blink on and off or just turn off and not come back on. So yeah, that's definitely something to keep an eye out on this thing for. And let's see here for the initial setup. So the way I have it set up is I have a little data structure that I have little unsigned integers for all the different settings, and I just go ahead and set those there. A lot of the examples I came across did show sort of spamming this clear screen or clear display and return home over and over just to make sure that it's set into some default mode. And then I just run this function here that just go ahead and runs a LCD command and sets all the different settings here. But so yeah, since this one has only 2 lines, I have to set the 2 lines. It has the 5x8 dots for each font. Runs in 4-bit mode. The display on will actually show the printed text on the screen. If this isn't set, then the screen will just not display anything, even though it is actually responding to your commands. And then yeah, the entry mode and stuff. So this will enter in from the left and right to the right. So it's a left to right writing, and that can be reversed if you have a right to left writing system you want to use. So for the next thing, I already showed that. Okay, we got the read control file. So I have a control file in there that you can write commands to and obviously read back what the current settings are. I haven't done a whole lot on this one. I've played with some of the settings on some, testing, stuff I wrote. But for this one here, basically I just have the option to have the backlight on or off, the display on or off, and also the ability to send a clear command, which will actually wipe the memory, any stored characters. So like when the display is off, it still stores everything. If you turn the display off, whatever's printed on there will vanish. If you turn the display back on, all that text will just reappear. So that basically will read from that struct I have, and just sort of mask out whether the display is on or not, and then print that out if you read the file. So it'll tell you if backlight's set to 1, display to 1, and clear always returns, it always says clear is 0. That's just to let you know that clear is a command you can write to it. On the right control end, so I take advantage of this little command buff and command tab. These are nice for basically breaking out, commands written to control files like this. So I can basically take the input data of whatever the count is, do a parse command, it'll shove it into this thing. Lookup command will take sort of a pre-configured, let's see, yeah, here we go, sort of pre-configured, command tab I have for whether you say, write in backlight equals, or just backlight space 1 or 0, clear display. So, what it corresponds to, which command, what the actual text of that command is, and then sort of the options. So there's going to be, 2, one for the name and a second one for the setting. Another thing I do here is I have to turn the string into an actual an integer to send off to the thing. So yeah, this will check to see which command I put in, then runs a little switch to go through each one. I basically have it set up so that like anything over 0 is a 1, and anything under 1 is off. Also have to remember that this also uses a malloc, so when you're done you have to free it. And here's where that returning characters helps for an error. So if for whatever reason you put in something other than the commands it recognizes, it'll say I don't understand as the error, and just frees the command buffer and then returns the error. If everything works, it'll go ahead and say that every bit that came in was successfully written, frees the command buffer, and returns with no error message. So let's see this LCD FS in action. So the default location will be in mount. That works. And both those files. And if I write clear 1, actually I'll do the others first. So I'll demonstrate the, if I set display 0 into the control file, makes the display look like it's blanked, but still stored in memory. So if I set it back to 1, all of it's still there. Could also change that to backlight. Let's set that to 0, and send that command. That turns the backlight off. I can then tell it to turn the backlight back on. And then the clear command, which actually sort of blanks any stored characters on the display. So to sort of demonstrate like what can be done with just sort of scripting it, I made a sort of banged out a quick little script here. So what this is going to do is if my SCD40, which is a sort of a combination temperature and CO2 sensor, is mounted, it'll read from that. It'll read the first line from this all file, which sort of lists out all the settings on it, and print that in row 1. In row 2, it's going to just every second, it'll print hours, minutes, seconds, sleep for 1 second, and then print the time again. So this will basically update every second. The SCD40 needs 5 seconds between reads. So then after 5 seconds, it'll do another read. This time it'll read the second line from all, and then go back to sort of printing stuff, just updating the time every second. So I can run SCD40FS. That's my file system I wrote a while back for this SCD40 sensor. I believe it's also mounted in mount. Yep, it's there too. So I should just be able to cat. It's the all file. So yeah, so the first line should write out the CO2, and the second line should write out the temperature. So I'll go ahead and run that, and my little LCD should start updating. And there it is. So it'll just print out the time, and then update, switch every 5 seconds between the current temperature and the current CP or CO2 in the room. You might notice there's some extra spaces between the CO and the equals because on the I went ahead and used, took advantage of the UTF-8 that's everywhere in Plan9 and 9Front, and used a little subscript 2 to be clever. But the fonts stored on this LCD display don't have one of those. So that bit of error checking I had earlier, where it would check to see if the value of the character being written wasn't a standard ASCII character, it would put a space in. And since this is UTF-8, it's probably taking 2 8-bit characters to write that subscript 2. So there's 2 spaces in there, or maybe even 3. Well, hard to say. And the same thing for the temperature. There's supposed to be the little degree symbol in there, which is missing too. But that's actually, it would be possible I could write a custom character and put it in there. And that is something that can be done. You can write little graphics things if you wanted to. But keep in mind the way it treats each cell as an individual 5x8, sort of bitmap. And so any bitmap you'd want to write in would have to be broken up into, 2x16, 5x8 blocks. And each one has to be put together that way. But hopefully this is sort of interesting. So just a demonstration of taking some device, exposing it as a file system. Matter of fact, 2 devices, a CO2 and temperature sensor, and then the output is a little LCD display. And actually updating the display just takes almost, an extremely simple script here. Because all I'm doing is, using sed to pull a specific line of text out of one file and just literally redirecting it to the file for row 1. The other one is just running the date command with the format option to just format the hours, minutes, seconds, and just dumps that into row 2. This is all just standard command line stuff. So yeah, it's very trivial to sort of use this file system abstraction to just make everything else easier after that. So, and as always, have fun.